Lesson 12.1 is typically how we have started out this chapter, introducing you guys to sequences and series, but there are some frustrating things that happen in 12.1 that we think having 12.2 and 12.3 under your belt first, so you know about arithmetic and geometric, then this will just be a breeze. So some of this is going to be review, which is nice, and just some definitions that originally we would have started you out with. A sequence, this is a function whose domain is a set of consecutive integers. Domain starts with 1 unless otherwise stated. And a term is going to be, the terms will be the values in the range. I'll talk about that more in the next slide. All right, so here's that domain. Domain is going to be, what you would plug in for n. If you plug in a 1 for n, you get back the first term, and that first term you get back is the range. When you plug in a 2 for n, so when you plug numbers in, that's a domain value you're plugging in. And whatever that output is that you get back is the range. A finite sequence has a limited number of terms, so you can see 2, 4, 6, 8, and it stops. An infinite sequence, it continues without stopping. So the difference here is, do you see after that 2, 4, 6, 8, if you see a dot, dot, dot on the end, that means that this pattern will continue forever. That's why it's an infinite sequence. So really just pay attention to whether or not it has a dot, dot, dot on the end to determine if it's a finite or an infinite sequence. So writing rules of a sequence, this you guys had the introduction to it with your MCA prep. So just to remind you, if you need the first term, that's a sub 1. This subscript means it's the first term. And you get that by plugging a 1 in for n. Oops, plus 5. Don't forget to write the whole thing. So 2 plus 5 is 7. So that's the first term of the sequence. Now if you want 4 terms, you have to also find a2, a3, and a4, and you plug in a 2, 3, and 4 for each term, or for plugging a 2, 3, and 4 into the rule to get each term back. So here's where this has had some frustrations in the past for students. When you're given a sequence and you have to kind of figure out what the pattern is, figure out what the next term will be, and then come up with a rule for it. So now that you guys know arithmetic and geometric, how those work, then those are what you'll check for first. If you see we have a 3, 8, 15, 24, is there any sort of consistent pattern here? So first check for geometric. 3 plus 5 is 8. And then plus 7 is 15. Plus 9 is 24. So we're not adding the same number. So we know it's not arithmetic. Could it be geometric? Are we multiplying by the same number? And I guess you could check to see if it's geometric by doing that. How do you show if something's geometric? You could take the 8, divide it by 3. That's the ratio between these two. Then you could take 15 and divide it by 8. And if any of those reduce, they should equal the same thing, which they don't, so that just means that it is not geometric either. So then we just really try to figure out what's the pattern here. And a lot of times it gets annoying and it gets frustrating, but we try to figure out what's happening. So we can see this is increasing by 5, increasing by 7, increasing by 9. If you were to guess what the next increase is, I would say 11. It seems to be increasing by odd numbers, which would make this next one 35. And this describing the pattern, I kind of have been doing that out loud. So to write a rule for the nth term, so write a rule that will give us any of these terms. Now here's where it's going to get frustrated, because how do you write a rule for this? It's not geometric, it's not arithmetic, so it doesn't follow those patterns. So here's the checklist I'm going to give you. If you have to do this on your own, which you will, first check for arithmetic, then check for geometric. If you can cross those off, then you know it's something else. After you have looked at those two, the next thing that's kind of common to see are patterns that deal with your perfect square numbers. And the only reason why I'm throwing this out there is because I've seen the homework. I know that that's a common way to write a pattern. So your perfect square numbers are 1, 4, 9, 16, 25. And if you look at the numbers that they gave us up there, they have a 3, and then an 8, and then a 15, and a 24. And do you see how these are all just one less in the perfect squares? So if I were to write a rule, maybe I would say, well, let's say you take n squared, but it's not just unsquared, we have to subtract 1 off of it. So n squared minus 1. And then to check to see if that works, I think that it's on the right track. Whether or not it's perfect yet, we'll see. A1, if you plug in a 1, we should get a 3 back. So 1 squared minus 1 actually is 0. So we have to think about how can we get back this 3. So this, what we're trying to figure out, we're seeing did not work. It's not n squared minus 1. But we feel pretty strongly that the n squared probably has something to do with it because of how close these are to those perfect square numbers. So here's where it's frustrating. I mean, it's a lot of guessing and checking. I actually just paused the video and guessed and checked a few things that I thought it might be and came up with n squared plus 2n. That's the rule that worked and gave me every single one. Now I will tell you that this is a more challenging example. Half the time what you see will either be arithmetic or it will be geometric, and you'll know exactly how to approach those. So some people are really good at this, some people struggle more with it. You just have to get through it as best you can and know that not every single example is like this, where, you know, we have some rule that looks like n squared plus 2n. All right, so let's move on to series. Now all of this is kind of review for you. A series is the expression when the terms of a sequence are added together. A finite series will look like this, 2 plus 4 plus 6 plus 8, where you're showing that you're adding those 4 terms. An infinite series is where you're going to have all those plus signs, but then plus, and you see the dot, dot, dot. That just means that that pattern continues, and we continue to add in every new term. The notation that we use is called summation notation. That's that sigma that we've been looking at in class a little bit. So on the bottom, typically we start with a 1 up to, this one is up to a 4 because there's only 4 terms. Over here you can see we started with 1 and went up to infinity because this one does continue forever. It's an infinite series. And then off on the right is always going to be the rule, whatever rule generates all those terms in a sequence. All right, so here are some examples where you probably haven't had a lot of practice with this yet. And we have to write the series using summation notation. So it's helpful to figure out, you know, maybe what kind of pattern is happening. We can see it looks like we're increasing by 25. And then we just want to know how many terms there are. So to write the summation notation, we start with sigma. We do have to figure out what the rule is off on the side over here. Well, if you're increasing by a fixed number like that, then we can start with 25n and then see if that works to give us all the terms. If you plug a 1 in for n, do you get 25? Yes. If you plug a 2 in for n, do you get 50? Yes. If you plug a 3 in for n, do you get 75? Yes. So we found the rule that works. Down here on the bottom, and by the way, you can use i's or n's. The variable doesn't really matter, but we'll start with a 1. And so the question is, how many terms are there? You know, if you plug in a 1, what number are we going to plug in that will get us up to 250? And so a few ways to think about it. I actually just took that 250 in my head and divided by 25 and got 10. So if you plug in a 1, you'll get that the first term, 2, 3, 4, 5, 6, all the way up to 10. That's how you end up with that 250. And so that's the answer. This is what summation notation looks like. For this next one, looks a little bit different, so I'm just going to start out with the sigma. Let's start with n equal to 1, and because of the dot, 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 it's going to go up to infinity. So that part, not too bad. So now we want to try to figure out what the pattern is here. And you can look at it separately. Look at just the numerators. You have a 1, 2, 3, 4. So if you're just increasing by 1, starting with a 1, you can just have an n up there. If you plug in a 1, you'll have a 1 up top. When you plug in a 2, you'll have a 2 up top. When you plug in a 3, so on and so forth. So that works out. The denominator, however, very similar. It's still increasing by 1. If I put an n down here, though, and you know that to find the first term you plug a 1 in, that's not going to get you to 2. If you plug in a 2, how do you get to 3? And then we say, oh, well, how about if we add 1 down there? Now that will get us all of those denominators. So anytime you're working with fractions, I would recommend dealing with the numerator and the denominator a little bit separately. See if you can find a pattern separately to write down that rule. All right, we won't do this whole example, but just to review how this works. Here's your summation notation. Here's the rule off on the side. If you have to do this by hand, you always start by plugging in the bottom number down here. So I know that we'll do 2 times 4 squared, and then you plug in a 5, and then how far do you keep going? Well, that's what the top number is for. That's going to tell you the last number that you plug in. So now we'll do 2 times 6 squared. You're going to find these 3 terms, and because they gave you summation notation, you will then find, that doesn't even look like close to spelling sum, you will find the sum. Again, I don't know what it is, but that's how you find it. All right, so here are definitely a few formulas to write down in your notes, well, along with everything else you've been doing. But if you have a special series, if the rule is a rule of 1 or I squared, you don't have to find these by hand. You don't have to get all the separate terms and add them up. These rules, it's not arithmetic or geometric, but because of the patterns that they form, they have some formulas which will work out quite nicely. This first one, if it's 1, that means that every single term is a 1 that you're finding. So if you're going from 1 up to 4, the rule says, oh, well, the sum will be 4 because you have 4 1s. Every single term is a 1. This next example, if the rule is I, and let's say you're going up to 4 again, well, your first term will be a 1, then you'll plug in a 2, then you'll plug in a 3, and then a 4, and then you would add those together. Now 1 through 4 is pretty quick. Maybe you'd add it together by hand, but if it was 1 through 30, you wouldn't want to be doing that by hand. So you would have to, or you would want to use the formula instead. This last one, I squared, what those terms will look like, you plug in a 1, and you have 1 squared plus 2 squared plus 3 squared plus 4 squared. Let's say we went up to 4 again. And then you would have to add those together or just plug in to the formula. Remember, n is number of terms. If you're going from 1 to 4, you'd plug a 4 into those n's and simplify. All right, last slide here. Here's just a few examples of the special series. And I need to try to remember what the formulas are. So what you do is you pay attention to what the rule is. Here's a rule of I, here's a rule of 1, here's a rule of I squared. Well, I know the rule of 1, the sum is just equal to n, and in this case, n is 15. So I know that that sum is 15. If I were to write out the series, every single term would be a 1. This one up here, n is 20, so what is it? 20 times 20 plus 1 over 2, and we would find the sum that way. Down here, n is 22, so we would take, just following the rule, 22 times 22 plus 1 times, I think this is 2n plus 1, so 2 times 22 plus 1 all over 6. So just have those the sum formula is handy so that you can plug in, that top number, which is the number of terms for each series. If it's a rule of 1, I, or I squared, we use those formulas instead.